slightly more ink flow. So this is a revision really. These are things you should know, but let us do it anyway. So here is a series 1 over 1 plus 1 over 2 plus 1 over 3 plus dot dot dot. This is called the harmonic series. Does it converge or does it diverge? You may remember that this one diverges. One way to see that it diverges is to look at this term and realize that, let's take this height as 1 and this as 1. It's a non-uniform scale. It is the area of this rectangle. Then half here is the area of this rectangle. That's half. Then similarly there is 1/3. There is another rectangle, then another one, and so on. Okay. Now this series is clearly the area of all these rectangles. What is this curve? This curve is 1 by x. Okay. So what is this curve? This curve is 1 by 1 plus x. The sum of the series is bigger than, let us say this is equal to s. S is bigger than the area under this curve. This is called the integral test actually. There is something, you can look it up. You need to revise these things. You're going to work on series, you should know elementary things about series. So s is now greater than the integral from 0 to infinity of 1 over this one, 1 plus x dx, but that is nothing but log of 1 plus x, the upper limit being infinity and the lower limit being 0, and that is infinity. So you see s is infinity. S is bigger than a series, bigger than a quantity that is itself infinity. So the series diverges. Very good. Let us now look at another series. 1 over 1 square plus 1 over 2 square plus 1 over 3 square and so on. Let this be S2. Okay. So now by similar reasoning, there is 1 and then there is 1/4 and there is 1/9 and so on. And if I draw it with yellow here, this curve is 1 by x square. If I draw it with red, this one passing through that point there, that one is 1 by 1 plus x square. Okay. Now S2 is bigger than 1 over 1 plus x square dx from 0 to infinity. We know this, okay, because it is just above, it's more than this area going to infinity. How much is this integral? It is 1 over 1 plus x minus 0 and infinity, which is equal to 1. Okay, because when x is infinity, that one is 0, and when x is 0, that one is 1. Negative here and a lower limit, so that is 1. However, s is also less than this plus that area, and that area we have just found, that is 1 there, and this is 1 also, and so S2 is between 1 and 2. Okay, now actually this is a well-known series, so if I go to Maple I will get an answer. And the answer is pi squared by 6. Pi squared is close to 10, so you can see that this number is in fact between 1 and 2 as we have estimated, okay, over here. So S2 actually happens to be pi square by 6. Okay, there is another kind of test. So this sort of test for convergence is called the integral test. There is another type of test for convergence which is called the ratio test. Okay, so if the nth term in a series satisfies this, the ratio of the n plus 1th term to the nth term, let this be Rn. If the limit as n goes to infinity of Rn is less than 1, then converges. If it is greater than 1, then diverges, and if it is equal to 1, then inconclusive. The test is inconclusive. We have to do further analysis. Now when you look at these series, they are sort of weakly convergent series. So what happens here is I have n Tn is equal to 1 by n square, and so Rn is equal to n square by n plus 1 square, which is equal to 1 over 1 plus 1 by n square, right? And then as we take the limit as n goes to infinity, this ratio is in fact 1. This one corresponds to this equality case. So this kind of series can be settled only with this integral test. It cannot be settled with the ratio test. However, there are other situations where the ratio test is very useful. So for example, I have a series, let us say f of x is equal to 1 plus x plus 2x square plus 3x cube plus dot dot dot. Here is a series. Okay, now what is this series? Whatever it may be, but when will it converge? So now I have Tn is equal to n x to the power n. Rn is equal to n plus 1 x to the power n plus 1 over n x to the power n, which is equal to 1 plus 1 by n times x. And then as I take the limit n goes to infinity of Rn, I simply get x. Well, let's say x is greater than 0. Okay, so then that I have x. Therefore, if I didn't have that, then I would just, if I did not have that, then I would just have that absolute value, then I would have that absolute value here, and then I would just have absolute value, right? So then for this series to converge, guaranteed if absolute value of x is less than 1. Okay, and divergence guaranteed if absolute value of x is more than 1. This reasoning works on the complex plane. Okay, why is that important? That's important because, for example, as you may know, 1 over 1 plus x square has no singularities on the real line, okay, but has singularities at plus minus I. Okay, this has a power series expansion which is 1 minus x square plus x to the power 4 minus x to the power 6 and so on, which we can check in Maple, for example. So I can say Taylor 1 by 1 plus x square x 13. You see, that's the power series. Alright, so it has this power series, and then you see convergence requires modulus of x less than 1. This is because on the complex x plane, so real part of x and imaginary part of x, there are singularities here and here at I and minus I. The series is about this point here at 0, and this is called the radius of convergence. This point, this is called the radius of convergence. Okay, so the radius of convergence is the distance to the nearest singularity in the complex plane, and that is why the radius of convergence is 1. Okay, now let me show you another related series. So we have done 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 and so on diverges. We have done 1 over 1 square plus 1 over 2 square plus 1 over 3 square plus, and this one converges. Let us try 1 over 1 to the 1.1 plus 1 over 2 to the 1.1 plus 1 over 3 to the 1.1 and so on. Okay, so let's call this series S1.1. By integral test, what we need is the integral from 0 to infinity of 1 over 1 plus x to the power 1.1 dx, which is the same as the integral from 1 to infinity of 1 over x to the 1.1 dx, which is the same as minus 10 over x to the power 0.1 from 1 to infinity, which is equal to 10. Okay, and so in fact, by similar reasoning, we know that 10 is less than S1.1 is less than 11. Similar to what? Similar to this reasoning that we were using here. Include this one and take this curve, otherwise take that curve. It's hard to see. I need to make it darker, then it may work. Take this curve. Okay. Alright. So we know that S 1.1 is between 10 and 11. So it is a convergent series. Suppose I sum it directly on a computer. I want the answer correct to 2 decimal places. So what I want to do is 1 over k to the 1.1. Sorry, I don't mean that. I mean this. Sum k from 1 to n. Okay. This is my approximation. Right? I want this from S 1.1. I want the difference to be less than 0.01. That's what I get when I have a second order, 2 decimal places accuracy. What is n? So I think you should guess, play a game. So since we are not in the classroom, I will have 1, 10, 10 to the power 2, 10 to the power 4, 10 to the power 8, 10 to the power 16, which is enough. You have to make a guess. Okay, and if you work it out, in fact the number is even bigger than this. It's quite a lot bigger. Just to show you that it doesn't work very well, let me use MATLAB, which is relatively quick. Okay, so what I say is, let us say n equals from 1 to 1e5. So I'm taking 1 lakh terms, and then I say sum 1 by n dot square. So this answer should be pi square by 6, which it is. You see, pi square by 6. That's what it is. Okay, so that it converges when this is 2. However, if I do the same with sum 1 by n to the power 1.1, I know the answer is between 10 and 11, but I get 7. Okay, so it's clearly I haven't taken enough terms. If I take, instead of 10 to the power 5, if I take 100 times more terms, that's a lot of terms. It is still 8.6. It is still far from 10. I have to take a lot of terms to get it there. In fact, the number of terms required, you can estimate it, and it is very large. The number of terms required is actually something like 10 to the power 30 terms. Okay, so although this is a convergent series, may not be very useful. Okay. Okay, that's another one observation. How about the series for e to the power x? E to the power x is 1 plus x by factorial 1 plus x squared by factorial 2 plus x cubed by factorial 3 plus dot dot dot, right? So this converges everywhere on the complex plane. Let us go to MATLAB and let's just try 1,000 terms. N equals 1 to 1,000. That's a lot of terms. There's no problem. Let us say x is 40, right? So what we will do is we will say sum of 40 to the power n oh, this won't work. Okay, what I will do is I will say s equals 0, I will say t equals 1, then I will say for k from 1, let's see, 1 to n, what is n? 1 to 100, I'll do 100 for the moment. T s equals s plus t, t equals t times x by k, end. Okay, all right. So I've taken a lot of terms. That didn't work. From is LaTeX. Sorry, from is maple. X equals 40. Okay, S. All right, exp 40. You see, the series works perfectly. Sorry for the small glitches, but But what about if x equals minus 40? Now s is this minus 126. It's clearly not correct, right? It's clearly not correct. Well, e to the minus 40 is positive and very, very small, right? So how come we got this large number? That is because in this series minus 40 there is a term which is 40 to the power 40 divided by factorial 40, right? So there is a term which is 40 to the power 40 divided by the product from 1 to 40. That term is there. Look at that term. That term is 10 to the power 16, right? Given that number itself is so big, right, and we are working with 16 places of decimals, then basically we just have junk errors after that. We don't have anything meaningful. Okay, we have lost all of that has to cancel perfectly and give you something that is 10 to the power minus 18. It is not possible. So this is another problem, is that with finite precision, see, this may not be very useful because of slow convergence. Additionally, with finite precision, we can have numerical errors. So in this example, for the exponential case, try x equals minus 40 and see on a computer. Okay, so these are some things about convergent series. Now let me show you something about asymptotic series. So for that we have to introduce asymptotic notation. Okay, so we are frequently interested in some small quantity, so we will say let x be small. Nothing is small by itself, so it is small compared to 1. We will write modulus absolute value of x much less than 1. We will write this. Okay, then what we say is, we say p of x, any quantity, could be a whatever, some constant, something depending on x, whatever, is order x if the limit as x goes to 0 of p over x by x is finite. Okay, so the limit may be 0, we still say it is order x. Limit may be finite and non-zero, we still say it is order x. Sometimes if the limit is 0, then we write like this. We say little o of x. Okay, sometimes we will say 1, so for example, x square is little o of x as x goes to 0, but sine of x is ox as x goes to 0, right? Cos of x is order 1 as x goes to 0. Sine of x is order tan of x as tan x goes to 0 or as x goes to 0. Okay, so we use notation like this. So sine of x by tan of x equals cosine of x, which goes to 1 as x goes to 0. So this limit is finite. Okay, so this order notation is very useful for us because we will write the following. Okay, so we will write it like this. A series f1 of x plus f2 of x plus f3 of x plus dot 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 is called asymptotic if limit x goes to 0 fk plus 1 by fk is equal to 0 for all k greater than equal to 1. That means, or same, f k plus 1 of x is equal to little o of f k of x as x goes to 0. Such a series is called asymptotic. What asymptotic means is that however this may behave, this is much smaller than this as x goes to 0. This is much smaller than this as x goes to 0. Okay, such a series is called asymptotic. A really important thing for you to understand is that convergent and asymptotic are two different things. Okay, so convergent series need not be asymptotic. Asymptotic series need not be convergent. So consider this convergent series: 1 over 1 square plus 1 over 2 square plus 1 over 3 square dot dot dot, right? So the third series, well, there isn't even a variable here, so that's a problem. But let us consider this series: 1 over 1 to the power 1 plus epsilon, 1 over 1 to the 2 to the power 1 plus epsilon, plus 1 over 3 to the power 1 plus epsilon. So for epsilon greater than 0, this is a convergent series. Yes, but if we look at the third term by the second term, it is 1 over 3 to the 1 plus epsilon over 1 over 2 to the 1 plus epsilon is equal to 2 by 3 to the power 1 plus epsilon, and as epsilon goes to 0, this thing just goes to 2 by 3, which is not 0. Therefore this is not asymptotic. Okay, it is convergent, but it is not asymptotic. All right. Now on the other hand, you can have an asymptotic series that is not convergent, and it is really important to understand this. Okay, so let us consider this. Let us say let f of a be equal to the integral from a to infinity of e to the power minus x by x dx. This is called the exponential integral. So you can see x is a dummy variable of integration, a is a parameter, so this is f of a, right? Now for any a greater than 0, f of a is finite, no problem. Okay, now we can develop a series for this by integration by parts. Okay, so the way we do it is we take this to be the first function, so we get 1 over x and then minus e to the power minus x, and we put a and infinity, then we put a minus, then we have the derivative of that, so that is minus 1 by x square, and then we have that integral which is minus e to the power minus x dx. Okay, a to infinity. That means f of a is equal to this. This is exact, there is no approximation, right? And what this one is equal to e to the power minus a over a, and what this one is minus the integral from a to infinity of e to the power minus x by x square dx. I want you to notice, please, that this is exact, there is no approximation. Okay, very good. Let's do it again. So when we do it again, then we have minus e to the power minus a over a from the first, then over here minus, and let me do this one, integration by parts. So I have 1 over x square e to the power minus x with a minus sign, a to infinity, then a minus, and then 1 over x square, the derivative of that is minus 2 over x cube, and minus e to the power minus x dx a to infinity. Tab. Okay, and so this should give me e to the power minus a by a minus e to the power minus a by a square, and then I think plus 2 e to the power minus a by a cube minus factorial 3 e to the power minus a by a to the power 4 plus some error term, and the error term is bounded. Okay, if I keep this error term with e, there is no approximation. It is exact. Okay, let's just check this series. Maple is good at calculating series like this. So let's go over here, and f is equal to integrate e to the power minus x by x equals a to infinity. And then let me say series f a equals, this is a series for large A, and there you go. The signs keep alternating, and here I have factorial 2, factorial 3, and so on. I can go little longer, and after factorial 3 this is factorial 4, you will recognize it, and then over here factorial 5, and so on. That's the series. Okay, so I hope you agree this is the series. Now this series is divergent, right? So what happens is Rn is Tn plus 1 over Tn, ratio test, is equal to, the exponentials cancel. Tn plus 1 means I have n plus 1 factorial by a to the power n plus 1, and then over here I have a to the power n factorial n. Okay, that's what I have, and so this is equal to n plus 1 over a, and then it doesn't matter how big a is. If I take n going to infinity, Rn goes to infinity because n is in the numerator, and therefore this series diverges. Okay, no matter how big a is, this series diverges. Okay, however n plus 1 over a goes to 0 for any n fixed as a goes to infinity, or as 1 over a goes to 0. Therefore this series is asymptotic for large A or small 1 by A. Okay, the idea is something like this. Okay, so suppose x is the term x, which here is 1 by a or something in this case, right? And here is the number of terms. So if you fix x and take more and more terms, then you need a convergent series. On the other hand, if you fix the number of terms and take x smaller and smaller, then you need an asymptotic series. So I hope this part is clear to you. The game is different. Okay, asymptotic series are in fact quite good. So if you come here, let us say, let me call this FA. Let me just take 3 terms. So that is a relatively small series. Let me say convert to a polynomial. And then, for example, if I say plot f and fa, and then I plot a equals 3 to 20, color equals red, blue, then the first one, the red one and the blue one, you see they match quite well. I should probably plot only till 8 or so that you can get a better picture. So you see it just converges, one converges to the other very fast. For large A, it is extremely accurate. If I go from 8 to 20, you will see that it is extremely accurate, right? If I go from, let us say, 13 to 20, you can't tell them apart anymore. By that time it has become small. It is true, this is a series for large A. When A is large, then this series, although truncated, is very good, very, very good. So that's what we are doing here, is in the asymptotic series, we always truncate an asymptotic series. And we always have to take a very large number of terms for a convergent series unless the series converges really rapidly. So I've given you an example of a convergent series that converges very slowly, and I've given you an example of an asymptotic series which is actually divergent. But when you fix the number of terms and you take a go to infinity or 1 by a go to 0, in that case you see that it gets better and better and better. Okay, so this is how we have to think about series when we develop approximate methods for solving nonlinear vibration problems, and that will be covered in the next topic, next lecture.